Hi guys, in this video let's talk about the problem trailing zeros in factorial of n. As per the problem description, we are given an integer n and we have to return the number of trailing zeros in factorial of n. So please note that your solution should be in logarithmic time complexity. As per the problem constraints, n lies between 1 to int max, and in the example input we are given n as 5. The example output is 1 because the factorial of 5 is 120. Here there is only one trailing 0. So therefore we will simply return 1. Now what is a trailing 0? So if you look at here and if you say there are 3 trailing zeros, then you are wrong. Why? Because a trailing 0 is the one which is at the rightmost end and that has no non-zero number to the right of it. So here there are only 2 trailing zeros. This will not be counted as a trailing 0. Let's see how can we approach this problem. So the brute force solution to this approach is that first we can calculate the factorial of n and then count trailing zeros in the result. So we can find the trailing zeros by repeatedly dividing the factorial by 10 till the remainder is 0. So what do we mean by that? So let's say the factorial, the n is equal to 10, and we'll do 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 and into 10. This will give us the number as 3628800. Now to find the trailing zeros, we will simply mod it with 10 to get the last digit. So we will get 0. Now since this is 0, we will simply increment our count. Next, we will divide the number by 10 to check the next number, the next digit, that means this number. So after dividing it, we will get nothing but 362880. So that means this digit has been removed, the last digit. Now we have got this. Now in the next iteration, we will simply do the mod of it to get the last digit. We got it as 0. So again, we will increment the count. Next, we will divide it by 10. Right, so here we have divided it by 10. Again find the mod of it and we get a non-zero number. That means here we have to stop because we have found out all the trailing zeros. And since we have got a non-zero numbers, that means we do not care what is there at the left of it, right? So we will simply stop and return the count. And this is what written in this snippet, that we have got the factorial as 120 of 5 when n is 5. So we will run our loop till this factorial is greater than 0. So if f mod 10 is equal to 0, we will simply count it up and we will divide f by 10. And else if it's not 0, then we will simply break because we do not care what is there on the left, and we will simply return the count. But the problem with this approach is that the above method can cause overflow for even slightly bigger numbers, as the factorial of a number is a big number. So even if the number is as small as, let's say, 22, then it's going to cause overflow because the factorial of even a small number is so big that it is certain to cause overflow, right? Therefore, this method is not the appropriate one. So what should we do now? Let's see what is a better approach. So how can we find a trailing zero in any number? So when a number is multiplied by 10, we get a trailing zero, right? So let's see 24. If it's multiplied by 10, we get 240. So here we have got a trailing zero just because we have multiplied it by 10. Then we have, let's say, 240, and if we multiply it by 10, we get 2400. We have got another zero which is contributed by this 10. Right, so in 2400, if we do into 10, we will get 24,000. So another zero which is contributed by 10. So here there is an observation to make that a number, if multiplied by 10, it will give us a trailing zero. So for example, if n is equal to 10, then we'll get this as this is the factorial of 10. So 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 into 10. The factorial is this, and we can see that there are two zeros, the two trailing zeros. That means there must be two tens, right? There must be number of tens is equal to 2 that are contributing to two zeros. So how are we getting that? So one 10 is here and 110 is formed by the combination of 2 and 5. So if we multiply 2 and 5, we'll get 110, right? So this is 110 and we will get 110 from here. So that accounts to 2 zeros. So this tells us that if in a number we look at the number of pairs of 2 into 5, then we'll be able to count the number of trailing zeros. So if in a number we look at that how many number of 2's are there and how many number of 5's are there, then we take the smaller number, we take the smaller power of a number. Let's say 2 is x and 5 is y. So let's say y is smaller than x, then we will take this, the number of 5's, and that is going to be the answer. Why? Because let's see with the help of this example. So in this case, the power of 2 is 3. That means there are number of 2's as 3. So this is 1 and 2 into 2 gives us 4. So 1, 2, 3. So there are 2 3's and 5 is just 1, right? So 5 will pair up with a single 2 to form a 10. Therefore, we will look at a lesser power from between 2 and 5, right? Now, do we really need to find the power of 2? Do we really need to find a power of 2? Well, here the observation is to be made that if we carefully look, then every second number is a multiple of 2 and every fifth number is a multiple of 5. So, if we are just able to find the power of 5, then they can pair up with that many number of 2's to produce a trailing 0. So let's look above with the help of example. So in this case, every alternative number, so this is a multiple of 2, then this is a multiple of 2, 6 is a multiple of 2, 8 is a multiple of 2, then 10 is a multiple of 2. So at every second number, we are able to find the multiple of 2, which will give us the number of 2's, right? That will give us the number of 2's. And every fifth number is going to be the multiple of 5 that will contribute to a power of 5, right? That will contribute to the power of 5. So as we can see that the number of multiples of 2 are greater than number of multiples of 5, that means we are going to get more number of 2's as compared to 5. So the number of 2's are going to be greater as compared to the number of 5. So we need not calculate the power of 2. Instead, we can simply calculate the number of 5's or the power of 5. So the problem has now reduced to finding the power of 5. So this is a generalized equation, like if we want to find a power of any number, then we can apply this formula. Here our x is equal to 5. So here we are actually trying to find the power of 5 and let this be any number, the remaining number which when multiplied with the power of 5 gives us factorial n. So how can we find the power of 5 or how can we calculate the number of 5? So for that purpose, we can simply take the floor of n by 5. For example, let's say n is equal to 11. Now n by 5 gives us 2.2. The floor of 2.2 is nothing but 2. That means the factorial of n is going to have 2 zeros. If we see here, then the factorial of 11 is nothing but 3991680. So there are 2 zeros, the 2 trailing zeros. Because in 11, how many multiples of 5 are there? It's 5 and 10. So this has contributed to 1 5 and this has contributed to 1 5. Therefore, the total number of 5's are 2 and therefore the trailing zeros are 2. But we are not through yet. Why? Because what about if n is equal to 28? What will happen in that case? So if n is equal to 28, so in 28 factorial, what are the multiples of 5? So the multiples of 5 are 5 itself, then 10, 15, 20 and 25. 5 will contribute to 1 5, then 10 will contribute to another 5, 15 another 5, 20 will also contribute to 1 5, but here 25 is going to contribute to 2 5's. So by taking floor of n by 5 with the formula n by 5 and taking floor of it, we'll get 1 5, right? So if we do n by 5, that means 28 by 5. This is going to give us 5 only, right? So that means here we are going to get just 5 zeros. But here we can see that there are 6 zeros in total. So for getting the left out 5, that means the 5 which is still to be counted, we'll have to divide it by next power of 5, which is 25. So now we actually have to calculate the power of 25. But now what about 128? So in that case, we'll get 125 as well in the multiples of 128 factorial, the multiples of 5 in 128 factorial. So it's going to be 5, 10, 15, then 20, 25, 30 and so on. Then 125 as well, right? So 125 has 3 number of 5s. So after dividing by 5 and then by 25, we'll still be left with one more 5. So for that, we'll have to divide it with the next power of 5, which is 125 to actually get the third 5. Now, the formula has become, so the count of number of 5s in prime factors of n factorial, it's equal to floor of n by 5 plus floor of n by 25 plus the floor of n by 125 and so on till the number is greater than n by power of 5. So the time complexity of this approach is going to be order of log base 5n. What was the question? That we have to find the logarithmic time complexity, and we have actually achieved that. So why? Because we are incrementally dividing n by powers of 5. So first we are dividing n by 5, then n by 25, then n by 125, so on till n by 5 to the power k, which reduces to 1, and n by 5 to the power k is equal to 1. So n is equal to 5 to the power k. After taking log both sides, we will get k as log base 5n. That means log base 5n number of steps we have to take to get the solution, and therefore the time complexity is going to be order of log base 5n. So this was it. Let's talk about the problem anagrams. So given an array of strings, you have to return all groups of strings that are anagrams. Represent a group by a list of integers representing the index in the original list. Let's look at this sample case for clarification. So an anagram is a word, a phrase or name formed by rearranging the letters of another. For example, spar and rasp. Both are anagrams because they have same set of characters, the frequency of characters are same, but only the order is different, right? Also note that all inputs will be in the lower case. So for example, the input is cat, dog, god and TCA. So you have to return 1, 4 and 2, 3. So basically we have cat over here, then dog, then god and TCA. So this is 1, 2, 3, 4. Right. So cat and TCA, they are anagrams because they have same set of characters. Even the frequency is same, but the order is different. Right. So we have taken them together. That means 1 and 4 are together. Likewise, dog and god, they both are anagrams because again the characters are same, the frequency is same, but the order is different. So 2 and 3 are anagrams. So we have to basically return the answer like this. Now here in the explanation, it's written that cat and TC are anagrams which correspond to index 1 and 4. Dog and god are another set of anagrams which correspond to index 2 and 3. So the indices are 1 based. The first element has index 1 instead of 0. So let's see how can we approach this problem. So the solution approach is that we can sort the given strings. Now how does this intuition came? So basically from the question itself, it said that anagrams are the words that have different order of the same set of characters. So if we sort both the strings, then if those strings become equal, that means they are anagrams, right? Because the order was different only, but they have same characters. So if we sort them, then the strings which are anagrams will become equal. And after that, we can simply group them together, right? So here we have got the input as act, DGO, DGO and act. So we have actually got them by sorting the individual strings given in the input. So ACT represents cat, DGO represents dog, and DGO again represents God, and ACT represents TCA, right? So we have basically sorted them. Now we know that a group of anagrams can be represented by a key, which is nothing but the string we get after sorting characters present in those strings, right? So here both cat and TCA are anagrams and they can be represented by a string which is ACT. So this we have got after sorting the characters present in them. So now to group the strings basically, we can perform hashing. So how can we do that? So a key can be the string, right? This unique string. Here the group of anagram is cat and TCA, right? So we can have a unique string for them which is ACT. Likewise for dog and God we can have a unique string as DGO. So we can have a string and then we can have value as vector of int because we have to basically keep track of the indices of the anagrams, right? So now we will simply iterate over this array, the sorted array. So first we are at act, then act is not present in our map. So let's put the string and the index present is 1. So let's put it in the vector, right? Now we are at DGO, right? So DGO is also not present in the map. So let's put it in the map and the frequency and the index present is 2. So let's put it in the vector. Now let's move ahead. So DGO is already present in the map. Now let's include the index, right? So we have included 3. Now we are at the 4th position and act is already present in the map. So let's simply include the index. So here we have the set of anagrams represented by their indices. Now the only task is which is left, that is to iterate over them and store it in the vector, right? So here we have vector 1 and 4 and we have a vector 2 and 3. So we will push them into a vector and we will simply return this in our answer, right? Also we will only put the vector in this resultant vector which have a size of greater than 1, right? If a string has size of just, so if the vector has size of just 1, then that means there is no anagram present for that particular string. So we can simply ignore that, right? So now for the time complexity, let's look at how we are going to sort the strings. So for sorting the string basically we can perform counting sort. We are able to perform counting sort because here the range of characters is fixed, right, which is 26. So we have 26 characters and therefore the complexity is going to be order of n into k, where n is the number of strings and k represents the length of the longest string. So the time complexity turns out to be order of n into k. Now if we don't want to sort the strings up, then we have another approach as well. So we can actually maintain a frequency array, right? Now what is a frequency array? So let's suppose we have this as a string. To form a frequency array of this, we will have a character set. We will have an array of 26 characters which have a range from 0 to 225. So why 26? Because we are in the input we are given that only lowercase alphabets will be there, right? So we maintain a frequency array of size 26. Now basically we will be mapping small a to index 0, then small b to index 1 and so on, and we will be representing small z by index 25. So basically here we will be storing the frequency of all the characters. So frequency of 0 denotes that it is the frequency of character a and so on. Here the frequency of a is nothing but 1. So we will put 1 over here. Then frequency, so basically we will be iterating over the string. So let's do that. So here b is there and frequency of b is nothing but 1. So at index 1 we will put 1. Now B is nothing but only 1. So let's put 1 at index 3, right? Then A is there, so let's put 1 at index 0. Then C is there, so let's put 1 at index 2. And E is there, so let's put 1 at index 4. Initially, all will be initialized to 0. So here's how we have built this frequency array, and likewise we can do for this string as well. And if the frequency array of both these strings come out to be equal, that means they are anagrams of each other. And likewise we can check this for all the strings given in the array. So for this purpose, we can basically have a map where the key can be, instead of string, it can be the vector of it. So here it represents the frequency array. The strings having the same frequency array will be pushed to the corresponding vector. So let's see how we will maintain this. So here we have cat, right? Frequency array for cat will look something like this. So here in this will be the key, right? Since was not present, so first we will be pushing it, right? And then we will be placing this one over here. Then we will be moving on to dog, and frequency array of this will look something like this, and we will simply put 2 over here, right? Then we will move on to God, right? The frequency array of God will look something like this, so we will put 3 over here. And for TCA, the frequency array will look something like this, so we will put 4 over here. So that's how we can do it, and then the last thing left will be to simply iterate this like we did previously and return the answer. The time complexity for this approach is going to be, so for creating frequency array for a string, it's going to be order of k, where k is the length of the string, and the total time complexity will be order of n into k, where n is the number of the strings, so it's going to be order of n into k. So this was it. Thank you so much.